everything. Now, if you are a fermion, you are neglected by nature, right? So you are always alone, in the best condition with a partner. So, this is the... He said that, right? No? He said that. So it is true. He showed that most part of the isotopes are bosons. He showed that nature like bosons. But the electrons are here, right? But they have charges, so. But the neutrons, they don't, and right? Anyway, the fermions always get together to make bosons because life is more pleasant when you are among friends and sharing things. Okay, so doing this deduction, I can end by having what we call the occupation number, which is in a quantum system, each state characterized by an energy epsilon I have an occupation number. And this is, of course, if it is plus or minus here, is what make a difference, if it is fermions or bosons. Now I would like to give you 10 minutes of how, in a simple way, you can calculate things on a boson system, right? And I'm going to just do two things. First is the occupation. We have a number of particles there. Second, because I want to give you some macroscopic properties, we're going to deal with the energy. But as you saw, there are many things to be worried about in a boson system. So the total number of particles is normally, or has to be, the sum of all the occupations. I have a number of particles in each state. If I add up everything, I end with my total number of particles. And energy is the same, but you introduce energy of each state in here. Turns out that we don't like to work in that way, or it's not so easy. And then we introduce the concept of density of state. Instead of having how many particles has this specific energy, I say, well, how many states I have around this energy? That's the density of state. And then I just say, well, each one has any epsilon occupation. And then normally introducing the concept of density of states, which is how many states are between energy E and E plus dE. I transform those sum in integrals. And to do that, I multiply by the number of states that you have in each interval dE, right? So I have this expression. But in doing this, as you know from principles of quantum mechanics, the density of states goes to 0 at the ground state. So when ρ is 0, I'm not considering that point in the integral. So I have to explicitly retain the particles that occupy the ground state. Which here, I'm going to say that the energy is 0 there. So this will be my starting point for energy. But that doesn't matter. You start the counting energy whatever you want. Okay, so this is the expression we have. And normally, the density of state depends on the potential, depends on basically the potential.
It depends on the dimensionality.
Oh, yeah, but that's involving the potential, right?
That graph sounds strange. How many dimensions you want?
No, this is 3-dimension. In 3 dimensions, if you go to 2 dimension, like the density state in a free gas is constant. So doesn't go to 0.
If I remember, ρe goes to E squared in 3 dimensions, right?
Oh, that's depending on the potential if you have. You have a harmonic or... say again, ρe goes to E squared. Yeah, and goes to 0 when E goes to 0.
That's the form of the graph.
Oh, no, the form, I don't know what potential I have. This is just a, this is just to show that goes to 0. Okay? The shape here, you see, is all imprecise. That's why, it can be this way, it can be root square, right? It can be anything. Depends on the confinement. So when I do that, I'm going to jump in this part. In cooling down the system, what's happening is that the first part of the integral, oops, I have to go back here. This first part of the integral, I have to say this, right? If I look at the occupation number, it normally has this shape and diverge. If you remember the occupation number, which is 1 over E to the epsilon minus mu. It diverges when you go to mu. But turns out that mu, which is the chemical potential that I should explain and I didn't, is not a state of your system, because we can show that's negative for boson system. So the system stops here. If I see the occupation number as a function of the states, it stops here. It would diverge there. But as I cool down, this point starts to approach to here, and eventually became the ground state. So at that point, the population diverge. You understand? Okay, so normally we say that Bose condensation will take place when mu became a real, the value of mu became a value of the real state of the system. Anyway, so I have those integrals. This is just to show to you the way we can calculate things. And this is normally very small. This is basically 0. Until one temperature, that's the temperature where mu comes and meets the ground state. In that case, this starts to build up. And the way that this build up, following this relation. Okay? So normally this is basically 0 for temperature above critical temperature, and is less than the, it builds up as an order parameter in a normal phase transition below the critical temperature. Yeah, because it's basically 0 and then suddenly appears, right? So the fraction of particles in the ground states is a kind of order parameter in this transition, right? Like the magnetization. How we calculate the density of state? Well, we go to the phase space, and as you know, for a given energy interval, the density in phase space, the area in phase space, or the volume, is related to the number of states you can have. So basically, the density of states is this integral here. So I consider in the phase space, and the possibility of occupying the phase space for my system is given by the energy, or the Hamiltonian. And if I vary my energy by d epsilon, I have this area here, and this divided by h cubic is the density of state. This is very much used in thermodynamics, statistical mechanics, right? Statistical mechanics is basically how you occupy phase space. This is the main principle. And if you do that, you can work out this energy, transform the units. Instead of expressing P and R, you're expressing energy and R. So you come with an integral. That's the density of state for any potential is given by this expression. So giving a potential, you determine the density of state. You determine the density of state, and the integral has to be done, of course, in the volume that this system can be accessed. And that's depending on the energy. So normally, if you forget about P, you make the energy equal to the potential. This provides you what is the available volume in phase space, in the coordinate, in the real coordinate for this particle. So normally we do that, and we have many examples like the box. If you do a box, the density of states goes with the root square of the energy. You do all the integral, and you find out that there is a point where that number starts to grow, and normally the temperature when that happens is when you have a 2.612 in density of phase space. And if you look what's happened, this fraction of particles is nothing, and at the critical temperature grows up very fast, and following a law, and this exponent depending on the potential too. Because as you saw, depending on the density of state. So for a harmonic oscillator, it's very nice because we can calculate, and how you find the critical temperature, you just make that integral and set the fraction of particles in the ground state equal to 0. You can get the critical, and the critical temperature for a harmonic oscillator that contains any particles is given by this expression. And the fraction grows below the critical temperature following a cubic law. Remember, the box was not cubic, it was 3/2. Huh? And we can do everything, and everything is done in this review I gave you. If if we consider a power law potential of any kind, you can just generalize and find out critical temperature in terms of this, and you can find out this population fraction in the ground states below the critical temperature in terms of this parameter. And this parameter is basically related to the...
I missed something, sorry.
You missed something.
Okay, what TC is that? What transition you are...
It's the point where the population accumulates macroscopically in the ground state. Okay? Well, that's the Bose condensation, right? Yeah. Is that from that point on, population grows in there. You understand? Yeah. I'm going very fast here too because I want to reach the other part. Maybe I'm not doing a good job here. Do I need to go back and then? No, it's okay? If you make a P, L, and Q goes to infinite, you recover what? If a P, L, and Q goes to infinite, what is this? It's a box. It's zero everywhere and goes to infinite when X just pass A. So this is a box of volume A, B, C. And if those guys goes to infinite, of course, this goes to half. Eta goes to half. And remember, the box was 3/2. Right? They're growing. So everything is very consistent here and everything. So this is expression of a critical temperature for any potential that is like a power law. And this is the law of growing the population in the ground state below the critical temperature. Okay. And we can use this and calculate a few thermodynamic properties like heat capacity. It is a macroscopic property, heat capacity, right? And you just integrate, and then you investigate, and has this nice shape. Remember, the critical temperature is the point where mu goes to 0. Mu is negative, and as the temperature decreases, approaches 0. When it reaches 0, and that happens in a finite temperature if the number of particles is big. Normally, it should be infinite, but, right? As Ketley said yesterday, 1,000 seems big enough.
So the fluctuation
10,000 even better.
so much important.
No.
You are far from thermodynamic limit for sure, but
Well, why?
if you have
Because the chemical potential goes 1 over n. So if it is 0, or if it is 10 to the minus 3, seems that the system accumulates everything and shows the phase transition. Because Bose condensation has been observed for 1,000 particles.
The partition function can be given as a sum over the states, and then you can include the next term in the states, and then you get this finite size effects that you're talking about, that will be neglected in the infinite particle limits.
Yeah. No, that's right. In fact, if you look in the little booklet I gave you, there is a final number of particle analysis where you can see the corrections that has to be introduced and everything. Okay. Finite size effects. Yeah. So this is a kind of overall, description of this. And so this is a kind of integral that's easy to make. You can find the heat capacity. It can have this shape or it can have this shape depending on the potential. And this is expected, right? Because what is heat capacity? Is the ability of the system to take energy from outside. And if you have a potential, depending on the shape, particles has to work against the potential to build up energy. So somehow it's very much expected that the heat capacity will depend on the potential you have. This is ideal gas. Huh? I explain interaction, then I come to the ideal, and now I go to the interacting Bose gas. And very interesting that depending on the power of your potential, there are a class of potentials depending on this eta, which is the sum of the inverses of the powers, that you have discontinuity in the phase transition, in the heat capacity, and for some numbers you don't have. And if you remember Ehrenfest kind of classification of phase transition that nobody uses anymore, right? Now is Landau kind of classification of phase transition. But if you remember the old way, that means changing the order of the phase transition. Well, low dimensions, I'm going to jump, I'm sorry. But you can have Bose condensation. Considering ideal gas and the simple analysis I'm making, you can have Bose condensation in 1 and 2 dimension. No problem. You cannot have in a homogeneous potential, but you can have in a non-homogeneous potential. And it's very interesting that anything that confines in 2 dimension allow you to have condensation. Now, in 1 dimension, you need a specific class of potentials to have. Okay? And I remember very clear reading papers that interactions in 1 dimension makes the same effect. So you start to have a possibility of Bose condensation in 1 dimension. But Ketley said that, no, that's not the case yesterday. So I endorse Ketley, of course. Now, what's happened if I have a potential? If I have a potential, and what's happening with the spatial density, right? So let's calculate. You know, the spatial density is the occupation number times the wave function square, and add over all the states. But I can do that in phase space too. If I go to phase space, right, the number of particles in some states are given by this term. If I divide by the volume, I have just the density. I have the contribution of the density due to the 1 energy or 1 momentum. If I sum over all possible momentums or energy, which means this integral, I calculate the spatial distribution of atoms in any potential. And if you do that for you choose what you want. For any potential, you can carry on this calculation, and I'm going a little fast in here, and you find out, but because you introduce that integral in phase space, again, the momentum 0 goes to 0, right? In this integral, when p equals to 0, this goes to 0. So when I do this, I'm leaving out the ground state. So I have to add that. And when I do add the ground state, well, this is an easy calculation to do. You exchange the integral by sum, and there are all geometric type of series you can analytically sum, and you can get an overall density profile which shows that at the critical temperature, there is a jump proportional to root square of n. And that's the jump that you see everywhere when the condensation happens, right? At the center appears that big peak due to the accumulation in the ground state. Again, I'm going fast to this because I want to go to the other parts. Okay, so this is the Bose condensation introduction. And now I would like to speak about interactions because we treat ideal gas, ideal system. But interactions are present. And normally to introduce the interaction in our relations, we put a term here that's proportional to the density. So it's like in each point, particle is filling the average field of the neighbors. No, wait. This is just the introduction of interaction. This is the energy of 1 particle in this system. If I have interaction, I can add this term. Right? What? This is a mean field. Yeah. Right? So if I put this term, this somehow represents the interaction. Whatever the density is higher in space, interactions play a more important role. And then I can use that semi-classical density that I calculate and come and even calculate for you the corrections that any potential you have due to the interaction in this building up of the ground state, or corrections in the critical temperature, and they agree more or less. It's not so bad. But we want to go further with this. When I did this, I put here gamma, right? Gamma somehow represents interaction. And interaction in the ultra low temperature means what? Scattering length. So gamma is related to scattering length. So let's find out who is gamma. And to find out who is gamma, we're going to do a small calculation here. We're going to imagine that we have a contact type of potential, delta potential, between the particles. And we're going to calculate what is the energy per particle that this potential introduces. So you just do the integration, right? You integrate in density. Imagine you have 1 particle here, right? Well, one particle somewhere here in a position R1, and it is surrounded by particles which coordinate R2, and if I integrate this, I'm getting how much energy per particle I have due to the interaction. And this is easy to do. Delta function is always easy to integrate. And you get that the energy per particle is half of V0 times the density. Okay? And what I put there as gamma is basically the energy per particle. So, gamma times n is how much energy per particle interaction is adding to the system. So this has to be equal to half of V0 n. V0 is that amplitude of the potential, of the contact potential. So I end up by having gamma. And V0, this is a delta potential. Everybody knows how to calculate phase shift and scattering length. It's in any book of quantum mechanics. And the relation between the amplitude of the delta potential with the scattering length is this. So I end up by having gamma. So gamma is proportional to the scattering length. Okay? And then I can rewrite all my expression, and the corrections come as powers of scattering length divided by de Broglie wavelength. Okay. Okay, but this is not enough. This is just a very simple approximation. We want to go a little farther. And then comes the equation of Gross-Pitaevsky. And this equation is basically on the spirit of the interaction. You already know that if I have interaction, and this is for 0 temperature now. So if I have a system that is described by, each particle is described by a wave function, phi square is like the density there, times the number of particles. So this A will have the number of particles in it. So, this is the new Hamiltonian if we have interaction. But of course, the wave function of my system, if I have any bosons there, right? The total wave function is the product of the individual wave functions. Then I'm going to take this. This is just the energy. It's not the wave function or anything. I take this and I create this functional. I say, well, each particle has this wave function. So let me calculate this. This is energy. May not be the energy of the system, but it's an energy. And then, as you learn from variational principle, I try to minimize this functional. Yeah.
In your last transparency, what happens in T equal to C for that region?
What term?
In the previous case, you had 0, right?
Oh, okay. So what I do here is the following. I calculate gamma, and then I come and I say, look, why I don't consider this as an effective potential? And then I do the semi-classical calculation again. And I can